What's up guys? Welcome back to Simple Science, where today we're going to be going over Unit 3, specifically everything you need to know about intermolecular forces. But before we get into Unit 3, there's just one important thing to go over that I didn't go over in Unit 2, and that's molecular polarity. So be sure to like, comment, subscribe, and comment any questions you have, and I'll be sure to get to them. And without further ado, let's get started. Last unit, we focused on the properties of different molecules, including the forces that hold a single molecule of a substance together, whether it was an ionic substance, a covalent substance, or a metallic substance. But in this unit, we're going to start out by talking about intermolecular forces, which are the forces that hold multiple different molecules together. And to do that, we first need to go over molecular polarity.
Molecular polarity refers to whether a covalent molecule is polar covalent or nonpolar covalent. And to figure that out, we first need to understand bond polarity. Last unit, we talked about how in a covalent bond, if there's a big electronegativity difference between the two atoms, the bond is polar. What this means is that the electrons in a bond are shared unevenly, with the more electronegative atom pulling the electrons towards itself. This makes the more electronegative atom partially negatively charged, and the less electronegative atom partially positively charged. This is called a bond dipole, where one side of the bond is partially positive and the other side is partially negative.
But how does the polarity of one bond affect the polarity of the whole molecule?
Well, if a molecule has multiple polar bonds that all pull electrons in a certain direction in a symmetrical shape, then those bond dipoles will cancel each other out, making the whole molecule nonpolar. This means that there is no partially negative or partially positive charged side of the molecule, and all the electrons in the covalent bonds are shared equally. Think about it this way. Let's say that you and your two friends are playing a game of tug of war. You hold two ropes and your friends are each pulling on a different rope. Your friends are both much stronger than you. But when the friends are pulling on the ropes from opposite ends, the ropes themselves end up going nowhere, since the force of the pulling cancels each other out. Now, replace you and your friends with atoms, with your friends being electronegative atoms, and replace the ropes with covalent bonds. Even though the bonds themselves are polar, since the electrons in the bonds are being pulled in opposite directions, the force of this pulling cancels out.
However, there is an exception to this. If the bond dipoles in a molecule are between different elements, the overall molecule is polar. Let me show you how that works with an example. This problem gives us the Lewis dot diagram for CH3O and asks us to determine if the molecule is polar or nonpolar. At first glance, from what we learned before, we would assume that the molecule is nonpolar. This is because the molecule is symmetrical, meaning that all the dipoles should cancel each other out. And that would be true if it weren't for this oxygen over here. The thing is, the bond dipoles in a molecule only cancel each other out if the dipoles are equal, aka if all the bonds are between the same two elements. The bond between oxygen and carbon is a lot more polar than the bond between all these hydrogens and this carbon, because oxygen is a lot more electronegative than carbon. So these dipoles are not equal. In this molecule, oxygen is going to pull all the electrons in the bond towards itself, making oxygen partially negative and carbon partially positive. Because one part of the molecule is partially negative and the other part is partially positive, this molecule is polar. Now, if this molecule looked something like ClO4-, then the dipoles would be equal since they were between the same two elements and they would cancel out.
Let's go back to the tug of war example. You and your two friends are playing tug of war again, but this time you invite a WWE wrestler to play with the third rope that you're going to hold. Sure, your friends are strong, but the wrestler is a lot stronger and ends up pulling all three ropes towards himself somehow. When talking about molecules, the wrestler would represent a different element that forms a bond with you, while both your friends would be the same element forming a bond with you.
The other type of polar molecule occurs when there's one or more lone pairs of electrons on the central atom.
Last unit, when we were drawing Lewis dot structures, we would sometimes put a lone pair of two unbonded electrons onto the central atom. That lone pair creates a partially negative charge on the central atom and a partially positive charge on the rest of the molecule. This is because the central atom has 2 additional electrons on it, making it negatively charged. This makes the molecule polar since there are partially negative and partially positive charges on the molecule.
Now, let's review how to tell whether a covalent molecule is polar or nonpolar.
If a covalent molecule has bond dipoles that cancel each other out, meaning that there's multiple polar bonds that are all between the same 2 elements, and it has no lone pairs on the central atom, then the molecule is nonpolar. If a covalent bond has multiple bond dipoles that don't cancel each other out, or if the covalent molecule has 1 or more lone pairs on the central atom, then the molecule is polar.
Now that we've talked about polar and nonpolar covalent molecules, we can start talking about intermolecular forces, which are the forces that hold covalent molecules together. And first, we're going to start by learning about London dispersion forces.
In chemistry, we learn that all electrons in an atom are arranged into energy levels and orbitals. But just because electrons are put into specific tiny energy levels doesn't mean they just sit in those energy levels like couch potatoes.
The truth is, electrons are always moving and going around and around the nucleus.
Now, let's say that you have an atom and all the electrons in that atom are moving. 1 second, all the electrons are pretty evenly distributed, but the next second, most of the electrons just randomly move to one side of the atom. Not for any reason, but just because they happen to be moving in the same direction. Because electrons are negatively charged, the side of the atom with the most of the electrons will have a partially negative charge, while the other side of the atom would have a partially positive charge. Now, let's say there are a bunch of atoms surrounding that one atom. The partially negative side of the atom would cause all the electrons in the other atom to move to the opposite side since negative charges repel other negative charges. This would create a partially positive charge in the other atom, and a partially negative charge in one atom would be attracted to the partially positive charge in the other, pulling them together. Now, this sudden dipole within the molecules creates a chain reaction with all the surrounding atoms getting a partially negative and partially positive side, and becoming attracted to each other. However, all of this happens only for a moment because, going back to the original atom here, the electrons will keep moving. So the partially negative side of the atom will go back to being neutral, getting rid of all the attractions in an instant. These temporary attractions between the molecules caused by the random movement of electrons are called London dispersion forces, aka LDFs.
Because all covalent molecules have atoms that are surrounded by an electron cloud, all covalent molecules have London dispersion forces. However, molecules with a larger electron cloud will have greater London dispersion forces than molecules with a smaller electron cloud. Let's look at an example. This problem asks us whether H2O, or aka water, or C5H12, aka pentane, has stronger London dispersion forces. Let's think about it. If London dispersion forces are caused by the random movement of electrons, then a molecule with more electrons will have stronger dispersion forces.
This is because the more electrons there are, the stronger the temporary dipole will be, since the negative charge will be greater on one side of the atom if more electrons go there.
Because pentane has more atoms than water, we can assume that it has more electrons than water. This means it has a more polarizable electron cloud, giving it stronger London dispersion forces. Now, electrons can move around pretty easily after forming these dipoles, which makes London dispersion forces temporary. And because they're temporary, LDFs are usually considered the weakest intermolecular force. Next, we're going to talk about a stronger intermolecular force, specifically dipole-dipole forces.
So we talked about polar molecules a couple minutes ago, with a partially positive side of the molecule and a partially negative side. Turns out that the partially negative side of one polar molecule can be attracted to the partially positive side of another polar molecule since opposite charges attract. The attraction between the partially positive and partially negative regions of a polar molecule are called dipole-dipole forces.
Because dipole-dipole forces are more permanent than LDFs, they're considered stronger than LDFs. In addition, While LDFs appear in all covalent molecules, dipole-dipole forces only occur in polar covalent molecules. Let's look at an example. This problem gives us the Lewis dot diagram for PCl3 and asks us what IMFs it has. It also asks us to draw another PCl3 molecules attracted to the first one using a dotted line to represent attraction. First of all, we know all molecules have London dispersion forces, since all molecules have an electron cloud that form temporary dipoles. So, we write down LDFs as one intermolecular force. Now, let's look at PCl3. There's a lone pair on the central atom, making it polar. This makes phosphorus partially negatively charged and the rest of the molecule partially positively charged. This means that in addition to LDFs, PCl3 also has dipole-dipole forces. Now we need to draw another PCl3 molecule attracted to the first one. Well, since phosphorus in PCl3 is negatively charged, it's going to be attracted to the partially positive part of the PCl3 molecule we're going to draw. So, drawing another PCl3 with one partially positive chlorine atom forming an attraction between phosphorus, we get a diagram like this. And the attraction that forms between phosphorus and this chlorine is the result of dipole-dipole forces. The last intermolecular force I'm going to tell you about are hydrogen bonds, which are kind of like dipole-dipole forces but on steroids. Now, you've probably heard of these bonds if you've ever taken biology, and to talk about them, I'm going to have to take you all the way back to the periodic table.
We've talked about electronegativity in Unit 2 a little bit, and how it increases as you go to the top and the right side of the periodic table. With that logic, nitrogen, oxygen, and fluorine are the three most electronegative atoms on the periodic table. So if either nitrogen, oxygen, or fluorine get into a bond with any other atom on the periodic table, the other atom probably won't even see the electrons. With that in mind, let's look at what happens when one of these three atoms forms a bond with hydrogen, which is one of the least electronegative atoms on the periodic table. And just like with our polar bonds, the fluorine, oxygen, or nitrogen, depending on which one it is, will be partially negative, and the hydrogen will be partially positive. However, because there's such a big electronegativity difference between hydrogen and the other atom, these partial charges become amped up. Hydrogen becomes extremely partially positive, and the other atom becomes extremely partially negative.
Now, let's look at what happens when a molecule with this type of bond interacts with another molecule with the same type of bond. This is a molecule of ammonia, which is NH3. As you can see, this is a polar molecule since there's a lone pair of electrons on the nitrogen. The bond between nitrogen and hydrogen is very polar, with the nitrogen being extremely partially negative and the hydrogen being extremely partially positive. When another NH3 molecule comes around, the nitrogen will also be extremely partially negative and the hydrogen will also be extremely partially positive. The partially negative nitrogen of this molecule forms a strong interaction to the partially positive hydrogen over here, creating a hydrogen bond between the two molecules. Now, you're probably thinking that this looks pretty similar to dipole-dipole forces. And you're right. Hydrogen bonds are just a really strong dipole-dipole force, which occur when an atom with either fluorine, oxygen, or nitrogen is bonded to hydrogen.
So, when we see a molecule that has hydrogen bonding, we also assume it has dipole-dipole forces and LDFs.
Now, let's go over the different IMFs that we've learned about.
We have London dispersion forces, which are the weakest, dipole-dipole forces, which are in the middle, and hydrogen bonds, which are the strongest. All molecules have LDFs, all polar molecules have dipole-dipole forces, and all polar molecules with a hydrogen bonded to either a nitrogen, oxygen, or fluorine have hydrogen bonds.
Intermolecular forces also affect things like boiling point and vapor pressure.
When covalent molecules are in their liquid state, intermolecular forces are holding the molecules together. In order to turn covalent molecules from a liquid to a gas, you have to boil them. Boiling the liquid breaks all the liquid's IMFs and turns it into a gas. The stronger the intermolecular forces are in a molecule, the higher its boiling point. with the boiling point being the temperature you need to heat a liquid up and boil it. A higher boiling point means that more heat energy is needed to break the IMFs in a liquid.
Let's do an example problem. This problem gives us the Lewis structures for PCl5, H2O, CH4, and SF2, and asks us to arrange them in order from least boiling point to the greatest boiling point. Molecules with a high boiling point have greater intermolecular forces, and molecules with lower boiling points have lower IMFs. So we need to look at the intermolecular forces present in each molecule. Let's start with PCl5. We know that all covalent molecules have London dispersion forces, so we write that down. We know it doesn't have any hydrogen bonding since there's no hydrogen bonded to either fluorine, oxygen, or nitrogen. To determine whether it has dipole-dipole forces, we need to see if PCl5 is polar or nonpolar. Well, all the dipoles in PCl5 are pulling in opposite directions, which means there's no partial negative or partial positive charges on the atom. There's also no lone pairs on the central atom, so PCl5 doesn't have any dipole-dipole forces. So the only thing PCl5 has is relatively weak IMFs. Now, let's look at H2O. Again, we know that every covalent molecule has LDFs, so we write that down. Here, we see that H2O has a hydrogen bonded to an oxygen, so it has hydrogen bonding, which is the strongest IMF. And because H2O has hydrogen bonding, it automatically has dipole-dipole forces too. Now, let's look at CH4. It has LDFs since it's a covalent molecule. There's no hydrogen bonded to either oxygen, nitrogen, or fluorine, so it doesn't have any hydrogen bonds. The bond between carbon and hydrogen is relatively nonpolar since they have similar electronegativities. There's no lone pairs on the central atom. And because of all this, we can say that CH4 doesn't have dipole-dipole forces and only has relatively weak LDFs. Finally, let's look at SF2. It has LDFs since it's a covalent molecule, and while there is a fluorine, there's no hydrogen bonded to it, so it doesn't have hydrogen bonding. And while the polar bonds between S and F do cancel each other out, the central sulfur atom has two lone pairs on it, making it partially negative and making the rest of the molecule partially positive. These partial charges mean that in addition to LDFs, SF2 has dipole-dipole forces. Now, let's take a look at the strength of each atom's IMFs and arrange them from having the lowest boiling point to the highest boiling point. Both CH4 and PCl5 only have LDFs, so they would be the two lowest. But which one would be lower than the other? Well, the strength of LDFs increases with a greater number of atoms in a molecule, since more atoms equals a larger electron cloud. PCl5 has 6 atoms, while CH4 has 5. This means that CH4 has the weakest LDFs, giving it the lowest boiling point, and giving PCl5 the second lowest boiling point. Now, let's take a look at SF2 and H2O. While SF2 has dipole-dipole forces as its strongest IMF, H2O has hydrogen bonding, which is stronger. So, SF2 will have the second highest boiling point, and H2O will have the highest boiling point. Next, we're going to talk about how IMFs affect vapor pressure.
Vapor pressure measures how much gas is in a container when the liquid form of a substance is at a certain temperature. If you put a liquid into a container, depending on the temperature, some of that liquid could get turned into a gas, since heat from the surroundings could heat up the liquid and turn it into a gas. The force that the gas exerts on the container is called vapor pressure. More gas will exert a higher vapor pressure, and less gas will exert a lower vapor pressure. Liquids that have higher IMFs will need more heat energy to be converted into a gas, so they typically have a lower vapor pressure. Meanwhile, liquids that have lower IMFs need less heat energy to turn into a gas, so they will have a higher vapor pressure.
Now, let's try to arrange the molecules from before in order of increasing vapor pressure instead of increasing boiling point. This is assuming that all the molecules are at the same temperature. The molecule with the strongest IMFs will have the lowest vapor pressure, assuming that all the different molecules are at the same temperature. In this case, water is the only molecule with hydrogen bonds, so it has the highest IMFs. This means it has the lowest vapor pressure. This means that compared to the other molecules, if liquid water is placed in a container at a given temperature, very few water molecules will get converted into a gas, since the IMFs holding the liquid together are so strong. SF2 has the second strongest IMFs, so it has the second lowest vapor pressure. PCl5 has the third strongest IMFs, so it has the second highest vapor pressure. And CH4 has the weakest IMFs, so it has the highest vapor pressure. Well, that was everything we need to go over for AP Chem Unit 3 about intermolecular forces. Next time, we're going to go over the properties of solids and all the different gas laws, which can be hard but pretty fun to learn. Make sure to drop any comments and questions that you have in the comment section below, and I'll be sure to get to them. Until next time, bye!